squared. The variance becomes larger with positive probability spread out more. The smallest variance that sigma squared that can assume is 0. And when would that happen? We'll discuss this when we get together. We'll go through an example. Something called the standard deviation of a random variable x is given by the square root of the variance. So just as a quick note, and I think when we go through this, when we're face-to-face in class, we do all this squaring because we want to make sure that we're not offsetting. You know, so if mu, my expected value turned out to be 4, and possible values for my random variable are 2 and 6, if I didn't square it, I could end up with a 2 minus 4, a minus 2 times the probability, and then I could have a 6 minus 4, which is the positive 2 times the probability. And what could happen is those could offset each other so that it zeroes out. And this is what the squaring element tries to get rid of, to make sure that we really capture the sense of variability that a random variable could take. Oops. Okay, so expected value example, going back to this and looking at what the variance would be. This goes back to that same example. You probably, if you calculated it through, the mean turned out to be 1.3. And the variance associated with the tool use would be calculated, again, just applying this formula, 0 times the mean, 1.3, square that value, multiply it against the probability that it's equal to 0, the random variable takes value, 0.1, and then 1, the value of the random variable, 1, minus the mean, 1.3, square that, multiply it times the probability that the random variable is equal to 1, plus 2 minus 1.3, square that, multiply it to the probability that the random variable is truly equal to 2, and that would be 0.4. Add those values up, we end up with a variance of 0.410. The second approach to calculating a variance, that was up on that previous slide. This is how we did it just a moment ago with the x minus mu squared. Now if you go over and you look at x, this other approach, which is summing up x squared times p of x, do that first. So in that case, sum of x, so we take x squared, x, the values that the random variable could take. So 0 squared times 0.1, probability that random variable equals 0. 1 squared times the probability that the random variable is equal to 1, that's 0.5. 2 squared times the probability that the random variable is equal to 2. And so you calculate what that all adds up to be, and that turns out to be 2.1. Now you take and you subtract off 1.3, which is the expected value squared, and you still end up with the same value of variance for this particular random variable as the probability, with this probability distribution function and described as being able to take values 0, 1, and 2. Okay, so that gives you a sense of probability, distribution function, expected values, and now we've looked at variance. Let's look a little bit, one more time at the same example. And here's where variance, and this is, I hope by giving this example, we'll give you a little flavor of, you could have, so let's say somebody goes back and looks at 10 years worth of records and found that out of 10 years worth of data collected, there was not a single day that there were no requests. It was always that people either requested the tool once during the day or twice during the day. And let's say, so our new probability distribution, let's say that instead it says, well, the probability that there were no requests was 0. Probability that there was 1 request during the day is now 0.7. And the probability that there was 2 requests during the day is now 0.3. If you calculated this out and said, 1, what's the expected value with this new probability distribution defined? You would say 1 times 0.7 plus 2 times 0.3. And what you would end up with is the same mean, 1.3. Now, how would the variance change? If we look at the variance of this one, we see that we would have 0 squared times 0 using this other formula, plus 1 squared times 0.7. The probability of the random variable equal to 1 is 0.7. The probability, and then taking the random variable 2, squaring that, times the probability that the random variable is equal to 2. You add all that up and you come up with 1.9. Then you subtract off. It's the same mean as before. And what we have is that the variance on this case now is 0.21. And remember that when we had probability distribution associated with this as 0.1, 0.5, 0.4, we had a variance of 0.41. Now we're looking at maybe a different 10 years or something, and we said that the probability distribution was 0, 0.7, and 0.3. Looking at that, just intuitively, what we have is that the second distribution, the 0.7 and the 0.3, there's a lot less variance. There's a lot less variability. It's cluttered more between 1 and 2 requests each day, as opposed to the first time when we looked at it with the 0.41 variance. That reflected that there was more variability in the number in the random variable values. And so that hopefully gives you a flavor of what variance is about. All right, at this point, break out, pause the tape, go try and take a shot at one of the textbook exercises. Linear functions of random variables. So this is actually just an extension of, it's an extension of the g of x that I mentioned a moment ago. But suppose that any random variable and constants a and b, that what this is e of g of x. But now what we're going to do is say it's a linear function with the ax plus b being defined as what g of x is. Then what we can find, and again, you could mathematically prove this out with a proof and everything like that. But this being introduction to probability and statistics, I'm going to give you a few of these where I'm just going to dump it on you and say, hey, this is what it is. So if you have a linear function of x, your random variable, and you know what a and b are, the expected value of ax plus b is equal to a times the expected value of x plus b. The variance of that function, g of x, in this case a linear relationship of ax plus b, the variance of that is going to be a squared times the variance of x. So if we go back to that same distribution, now back all the way to the original with the probability equal to 0.1, 0.5, and 0.4, then what we have is we noted that the e of 10x, now we go back to having $10, 10x as our g of x. We noted that the mean, the mu, when it was just, we didn't look at dollars, we just said the number of times the tool is requested in the day. We said that mean, mu, was 1.3. We noted that now what we have is e of 10x is equal to 10 mu, which is $13. So that's one thing we just had on the previous slide. Similarly, we found that the variance of this distribution for this particular random variable was 0.41. Now, by the previous slide in the formula, we had that variance of 10x is going to be a squared times the variance of x, which is now a would be 10, so you square that, times the variance of x, which is 0.41, and you end up with a variance of 41. And if you think about it, so the dollars, so the average value of your budget would be $13 with a variance of 41. Okay. Example of learning checkpoint, and again, you have the solution slides to these, so just to checkpoint in that you're grasping these different, different concepts. 2 construction contracts are to be randomly assigned to one or more of 3 firms. 1, 2,